So here in this video, I will give you a simple example of non-convex optimization problem. Here we are considering some input and output pair of dataset, and then we want to find out some linear fitting model that can explain input and output pairs. So for instance, if we consider a very simple linear model with a d-dimensional parameter w, so basically here we mapping output y equal to the parameter w and xi input multiplications on in the product plus some noise. So this is linear regression, and we find the model parameter w using this optimization problem, linear regression problem. Okay. So this simple, very simple model, linear regression model is so here this is the objective function, and fortunately with this simple linear regression model, the objective function is convex. So why this is convex? So let's say this is fw function. Then when you compute the Hessian of fw, so this is equal to 2 times summation I equal to 1 to n xi transpose. Okay, so this is positive semi-definite matrix. xi transpose is positive semi-definite matrix, and sum of positive semi-definite matrix is also positive semi-definite. So Hessian is positive semi-definite, which means all eigenvalue is non-negative, all eigenvalues are non-negative. Then this is convex optimization problem. So because this is convex optimization function with respect to w, the model parameter, so using gradient descent approach, we can converge to global optimal that describe input and output pair very well. Now let's consider linear neural network model. So this mimic our deep learning models without any activation function. So basically, the linear neural net just multiply the weight matrix of each layer. So because this is again regression problem, the objective function can be written like this: sum from I1 to n. So over a whole training data point, we try to measure the distance between our estimation by linear neural net and the true label yi. So wl times wl minus 1 times w1 xi minus yi norm square is the distance between our function output, the linear neural net output, and the true labels. And we want to minimize this distance scale. Right. Then let's say this is a function of your parameters wl minus 1 w1. So is this convex? No, unfortunately this is non-convex problem. So linear neural net problem is non-convex problem. So we can very easily check this, and let's consider a very simple model such that all matrices are 1 by 1 and having only one data point, x1 and y1, and x1 is equal to 1 and y1 equal to 1. So consider very simple model, right? So then, oh sorry, there is no such summation. So our running process again define an objective function, and we want to find the parameters that minimize the objective function. So w1 star up to wl star will be the solution of this objective function, and that minimize the objective function. Okay. So this is non-convex still. So when you compute the gradient of fw vector, then this is 2 times wl to W1 minus 1 times the vector WL up to W2, WL up to W3 times W1, WL, W4, W2, W1, and so on. So in the end, we have WL minus 1 to W1. Okay. And then when you compute the Hessian, you can easily find some example where the Hessian have negative eigenvalue. Okay, right. So this is non-convex problem, so we cannot guarantee global optimality from any initial point. So, no, say again. So there exists some initial point that can converge to the global optima with gradient descent with nice step size. But there are also other initial points. Starting from there, your optimization process converges to some very bad local minima. Okay, so basically the global optimal hold when WL times W1 up to W1 equal to 1. When this hold, your gradient is equal to 0, and also the objective function is equal to 0 as well, and the zero objective function, so zero error means the best parameter, the global optimal parameter, because we cannot make the objective function below 0 because there is square rule is non-negative, right? But there are also other type of local minima such that some W values, like for instance W1 equal to W2 equal to 0, then your gradient vector is equal to 0, right? So more than two parameters having 0 value, then the gradient vector is equal to 0. That is local minima. And at that point, your loss function is 1, not 0. So here, your output mapping does not explain your input and output pair, but just make trivial output 0. Even the previous example, more complicated example, more than two layer having 0 matrix, then your gradient vector is just simply 0, and your parameter stuck there, and you are just making very trivial output y equal to 0. Okay, so this is very bad. So we want to make some optimization process escaping from such a bad local minima. So many papers try to explain from some subset of initial point, the convergence behavior follows some nice path, and we can guarantee something. Okay. For instance, in this case, we can explain the convergence behavior using some C-balanced concept. C-balanced concept means all Wi value having this property. So for any pair of I and j, one parameter cannot be bigger than more than c times another parameter. Okay, sorry, this is wj. So when you pick any parameter, this parameter cannot be bigger than some constant times another parameter. So which means your parameters are very well balanced. Okay, and also this also means your parameter does not have 0 value. With this condition. So when your parameter value is non-zero and C-balanced condition, and if we can say your all path, your all trajectory always satisfy this C-balanced condition, then at least we can say that our path does not converge to this very bad local minima. right? And this is easy to check when you have C-balanced conditions. So for instance, W0 satisfy C-balanced point. Then basically from the gradient shape, we also say that W1 is C-balanced. So in other words, when WT is C-balanced, then WT plus 1 is also C-balanced. Then we can say that our trajectory always belong to C-balanced subset of parameters. So we can utilize very nice properties of C-balanced subset. Okay, so that is one possible way to deal with non-convex optimization problem. When you have some parameter area that having very bad properties, then at least we can try this. We can define very nice subset of parameters and just utilize the very small subset. Then maybe you can find a very nice way to guarantee global optimality.